Welcome back. The final example of this series will demonstrate Hooke's law. Let's go ahead and read the problem statement. By the way, this problem is from Mechanics of Materials by Timothy Philpott, Wiley, 3rd edition. The 16 by 22 by 25 millimeter rubber blocks shown in the figure, that's these blocks right here, are used in a double U shear mount to isolate the vibration of a machine from its supports. An applied load of P equals 285 Newton causes the upper frame to be deflected downward by 5 millimeters. Determine the shear modulus G of the rubber blocks. Okay, so we have some nice figures here. Let's go ahead and draw our additional figures and try to figure out what's going on. A side view of the mount. We have a downward load P, okay, which is going to be balanced by shear forces on each side that are transferred to the rubber blocks. I'll label those shear forces as V, and from simple equilibrium consideration we could deduce that those shear forces V are equal to the applied load divided by 2. This is the frame specimen. Okay, then next to the frame we have these rubber blocks, and let's go ahead and draw a picture of one of the deformed rubber blocks. Okay, it's deformed in shear, so in other words it has applied shear force on each side, and the dimensions of the block from the side view are this dimension 16 millimeters, this dimension before being deformed is 22 millimeters, and then we're also given the information that the upper frame is deflected downward by 5 millimeters. So in other words, this downward movement delta equals 5 millimeters. Okay? As far as the shear strain in the system, that would be the angle gamma that results from that deflection. As a summary of the given information, we are given delta 5 millimeters, downward deflection 5 millimeters, P equals 285 newtons, and the block dimensions, which we have to do a little bit more work to interpret, but they are 16 by 22 by 25 millimeters, and we'll have to use that information to determine the relative shear area for the problem. Okay, so what we are asked to find is the shear modulus G, and again, shear modulus of elasticity have units of stress. Since we're working in standard units, I'm going to express this in most likely megapascals. Sometimes for shear modulus we would use gigapascals because they tend to be very large in megapascals, but this isn't true for rubber, which is a relatively flexible material. How do we find modulus, the shear modulus? We need to consider Hooke's law in shear, which says that tau is equal to G times gamma. So we can find G by finding the stress and the strain in the system. Let's start with the stress. Shear stress is equal to the shear force divided by the shear area. We already noted that the shear force was equal to P over 2, or 285 divided by 2 newtons. And the shear area is going to be the area of the interface that interfaces with the mount on the right side. So not the thickness, but the height times the width. So those dimensions, height of 22 and a width of 25 millimeters squared. Okay, doing our calculations. This is 0.259 newtons per millimeter squared, or megapascals. Now, the shear strain is this angle gamma drawn in the picture up here. From geometry, we observe that the tan of that angle gamma is equal to 5 divided by 16. This is not a small angle assumption, so I'll have to solve. Plugging that into a calculator, we can find that gamma is equal to 0.303 radians. And for applying in this equation, we definitely need gamma to be in units of radians. That's the dimensionless quantity that's relevant for the problem. So now we have everything we need. Tau is equal to, G is equal to tau 0.259 megapascals divided by gamma 0.303 radians, which gives an answer of 0.855 megapascals. The units are right. The number is small for an engineering material, but makes sense since the material is rubber.